This video is going to look at the first formula for building confidence intervals that is used when either you know the population standard deviation or you have a large sample. And to do that, we're going to walk through example 1. Okay, a study of 35 adult females from a certain population showed the mean systolic blood pressure to be 116.0 millimeters mercury and the standard deviation to be 8.4. Find the 95% confidence interval for the true mean. So we want to find a range, make an interval estimate that we're 95% sure will contain the true mean. Now, before we go to the actual solution, I want to call your attention to the rounding rule that basically says we want to work with one more decimal place than the raw data. And if you think about it, what that means is we're essentially going to match the mean and standard deviation because that's the same rounding rule we had with those. And you'll see this formula when we go to the solutions. All right, so same problem. The formula, when you first look at it, there's a good bit of notation here, but it breaks down fairly straightforward. In the center, we have less than mu is less than. We're trying to figure out the range for mu. So we're looking below this first less than, to the left of this first less than is the lower limit. Above this upper less than is the upper limit. So what we have to do is figure out what goes in each of these pigeonholes, what each of these values are. Okay, first off, x over bar we've seen before. That's the sample mean. So if we go back to the problem, 116.0 is the sample mean. So you can pull those out. I'm going to skip over z of alpha over 2 for just a second. Sigma is the population standard deviation. So if we have the population standard deviation, we use that. In this case, though, we don't have the population standard deviation, but what we do have is a large sample and the sample standard deviation. So in that case, we can substitute that in for sigma. N is the sample size, plug 35 in for that. So we've covered 3 of the 4 pieces. The fourth piece is this z of alpha over 2. And before I move forward, alpha, you may have seen in the book, is basically the probability that our interval does not contain the true mean. And the thing you need to realize is alpha and your confidence interval total 1 or 100%. So with a 95% confidence interval, your alpha is essentially 5% that the mean isn't in there. So what we want to do is we want to find z values such that the range contains 95% between them. And we want it centered on the mean. So essentially what we want to do is break down the normal distribution to where we have 2.5% in the left tail, 2.5% in the right tail, and 95% in the middle. We want the narrowest range to do that. And if you start looking at the z-table, and if you think back to the chapter 6 examples we had done, we did example 9, and we found the area between negative 1.96 and positive 1.96. That example was chosen for a reason, because that number comes back here. When you're doing a large sample or known standard deviation example, and you want a 95% confidence interval, this z of alpha over 2 number will always go to 1.960. Now, there are a couple ways you can do that. You can either realize what I just talked through with the example 9 that we had done in the previous chapter. You can work with the z-table and find it, and kind of work backwards and find, okay, where's 0.250, where's 97, or 0.9750. Or the other thing you can do is you can go to the t-table in the book, and we'll see the t-table in a few minutes, but you can actually go all the way to the bottom row of that table where you see a z or infinity, and you can use that table to dig out the 1.960, which is what I did here. But this is one of those things that the nice thing is, if you are using this version of the formula for a 95% confidence interval, this is always 1.960 and minus 1.960. All right, now we have to do some arithmetic. 1.960 times 8.4 divided by 35 square root is equal to 2.7829, and my calculator keeps on going. We only want one decimal place because we want to match what the mean and standard deviation had done, so we round that 2.78 down to 2.8, or I'm sorry, up to 2.8. more accurately. Once you've reached this point, you now have two choices for how to finish the problem. You can either do the arithmetic, so it's take the 116 minus 2.8, get 113.2. Do the addition on the other side, 118.8, and this is one form of your final answer. 113.2 is less than mu is less than 118.8. Alternatively, you could take and express it as mu equals this 116.0 plus or minus 2.8. You know, some people prefer the first one, some people prefer the second one. They are equivalent.